Alright, in this video we're going to talk about Unit 5, Objective 2, Finding Limits Algebraically. So in the last section we looked at finding limits graphically and numerically, so we would look at a number on a chart or look at a number on a graph and try to find out what value, y value we're getting really close to. But in this one we're going to learn to use algebra and derivatives to find our limits. So since the limit's just telling us what y value we're approaching, sometimes if it's just a normal function, a nice function, we can just plug in the x value that we're approaching. And if there's no holes or anything, not a piecewise function, generally speaking, we're just going to get our answer out. Now, AP's not going to give us anything that easy, but it's a good start, because most of the ones that AP is going to give us are going to have a removable discontinuity at that x value. And those are going to show up in a very unique way on our limits. So what they're going to show up as is something called an indeterminate form. So what we're going to do is, again, we're going to plug in our x value. If we get an answer out, that's fantastic. That's the answer of the limit, because the y value is going to approach the actual y value. But that's not going to happen very often. We're going to end up having some sort of removable discontinuity or maybe an asymptote. And those are going to show up when we plug in our x value as an indeterminate form. Now, there are a bunch of different indeterminate forms, and there's a list of them right here. So anytime we have something 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, 0 times infinity, 1 to the infinity, 0 to the infinity, just plain old infinity or just plain old negative infinity, those are called indeterminate forms. So when finding limits, they're not going to guarantee us that a limit exists, nor are they going to tell us what the limit is if one exists. But a lot of times if we get one of those indeterminate forms, we're going to get an answer. We're going to be able to find a limit, even though it doesn't necessarily guarantee. These last two here, infinity and negative infinity, those are the ones that are going to make it to where we probably aren't going to have an answer. But the other ones are going to give us, probably we're going to get an answer. So any of these first set here, we're probably going to come up with an answer after we do a little bit of calculus, L'Hopital's rule. Now, something that I want to point out, if a is equal to 0, 0 over 0 is undefined. It's one of these undeterminate, or I'm sorry, is not equal to 0. That's what it should say. If a is not equal to 0, so a number over 0 is undefined, 0 over a number is 0, and then 0 over 0 is one of these indeterminate forms. So how we're going to deal with our indeterminate forms is something called L'Hopital's rule. So you can read this big long thing here and figure out what L'Hopital's rule is, but the long and short of it is, if the limit gives you an indeterminate form, so any of these things here, we're allowed to just take the derivative of the top part, take the derivative of the bottom part, and then take the limit again. So we're taking the limits of these things separately. We're not going to do quotient rule, but it's going to be the derivative of the top part, the derivative of the bottom part, and then take your derivative again. Now notice one thing up here, note up here 0 times infinity. We're going to rewrite it as 0 over 0 or infinity over infinity, and I'll show you an example or two that kind of deal with that. And the reason we want it in one of these two forms with division is so we can use our L'Hopital's rule. L'Hopital's rule only works if we have a fraction. So there are some quick, straightforward problems on here that we can run through. So we always want to start by plugging in this x value and see what happens. So if we plug that in, we get e to the 0, which is 1, minus 1 is 0, over 0. So that's going to give me an indeterminate form. 0 over 0 is indeterminate, so what we can do instead is take the limit as x approaches infinity of the derivative of the top. So the derivative of e to the 2x is going to be 2e to the 2x. Minus 1 is just going to be 0. Derivative of the denominator is 1, so we're really dividing by 1. Then we take the limit again, so take 0, plug it in. 2 times 0 is 0, e to the 0 is 1, 1 times 2 is 2, so our limit is 2. So looking at the next one, limit as x goes to infinity of natural log of x over x. So that's going to give us natural log of infinity is going to be infinity. It's going to take a while to get there, but it's going to be infinity. over just infinity. So it's another indeterminate form. So we're going to end up taking the limit as x approaches infinity of the derivative of the top, 1 over x, divided by the derivative of the bottom, 1. So again, we're not doing quotient rule. We're taking the derivatives of the top and bottom separately. So then we take our limit again. So we have 1 over infinity. Now, if you look back at your indeterminate forms, 1 over infinity is not indeterminate. 1 over a really big number like infinity is 0. So a way to think about this is if you do 1 divided by 1, you get 1. 1 divided by 10, you get 0.1. 1 divided by 100, you get 0.01. So as this number gets bigger, the entire fraction gets smaller. Well, if we get so big as to call it infinity in our denominator, we're going to have 0 for our answer. Now, number 3, again, let's take these, plug it in. So we're going to get negative infinity squared is going to give us a positive infinity. E to the negative times negative infinity. Negative times negative is going to be a positive. E to the infinity is infinity. So we get infinity over infinity. That's indeterminate. So we're going to take the derivatives of the numerator and the denominator. So we're going to get 2x over negative e to the negative x. Plug in infinity or negative infinity again. So we're going to get negative infinity over negative infinity, indeterminate. So let's do L'Hopital's rule again. This time we're just going to get a 2 over e to the negative infinity. And then e to the negative infinity, let's plug negative infinity here. Negative times negative again is going to be a positive infinity, right? So we're looking at 2 over infinity. And just like 1 over infinity here was 0, 2 over infinity is still going to be 0. Now if we look at this one, we're going to have e to the negative infinity times the square root of infinity. Well, e to the negative infinity is really 1 over e to the infinity, so that's going to be 0 times infinity. So that note on our indeterminate form said, if you have 0 times infinity, we need to rewrite the problem before we take our derivative to make it 0 over 0 or infinity over infinity. So instead of having e to the negative x, let's move that down to our denominator. And we can rewrite this as square root of x over e to the x. And if we plug in infinity, we're going to get, in this case, infinity over infinity. So now we can use our L'Hopital's rule. So the derivative of the top is going to be 1/2 x to the negative 1/2. The derivative of the bottom is e to the x. We can rewrite this. We have x to the negative 1/2. So we can write this as like 1/2 over e to the x times the square root of x. So if we're taking the limit as x approaches infinity of this, we're going to have 1/2 over infinity times infinity, which is 1/2 over infinity, which is going to be 0, like all these other ones that had a number over infinity. So there's one more question, and then we'll call it quits on this video. So the population of a bacterial colony is measured in thousands and is given by P of t equals 10 plus t sine of 1 over t. Find the maximum limits on the population of the colony. So maximum limits would be as time goes to infinity. So what is the limit as time goes to infinity of P of t is what this question is asking. So if we replace P of t with 10 plus t sine of 1 over t, I have addition, so we can split this up into two separate limits. So the t limit as t goes to infinity of 10 plus the limit as t goes to infinity of t sine of 1 over t. So this is just going to be 10, right? There's no t to plug in here. So this answer is just going to be 10. Right, can't plug infinity in for anything, so we're left with just 10. If I plug infinity into this piece, I'm going to get infinity. 1 over infinity is 0. Sine of 0 is 0. So I have infinity times 0. So we need to rewrite this problem So it's either infinity over infinity or 0 over 0. So we have two choices. We can write this as the limit as t approaches infinity of sine of 1 over t divided by 1 over t, right? So if we are dividing by 1 over t, we're multiplying by the reciprocal, so we're multiplying by t. So really this is another way to write it. Or you can take the same approach and write this as t over cosecant of 1 over t, but then our derivatives get messy and we don't really want to deal with that. So if we plug 0 in, we plug infinity in, 1 over infinity is 0, sine of 0 is 0, 1 over infinity is 0, so we have 0 divided by 0. So that's something that we can use L'Hopital's rule on. So the derivative of, if we think about 1 over t as t to the negative 1, of sine of 1 over t is going to be the derivative of this, which is going to be negative t to the negative second. So negative t to the negative second cosine of 1 over t. Derivative of the bottom, well, 1 over t is the same thing over here, so we can think of that as negative t to the negative second. If we look at what we have right now, we can simplify a little bit. I can take this, cancel it out with this. So we're really looking at just the limit as t approaches infinity of cosine of 1 over t. Well, if t is infinity, 1 over infinity is 0, cosine of 0 is 1. So this whole piece here is 1, that piece there is 11. So our maximum population is 11,000, since they're telling us measured in thousands. So that'll call it quits on that video, and we'll see you in the next one.